Probability is the mathematics that helps us measure and understand chance in our daily lives. When we roll dice or flip coins, we can't be certain about the outcome beforehand. These are perfect examples of randomness that probability helps us describe mathematically. Even though we can't predict the exact outcome of a single roll or flip, probability allows us to understand the pattern of results over many trials. The fundamental definition of probability is quite simple. It's the ratio of favorable outcomes to the total number of possible outcomes. This gives us a way to measure how likely an event is to occur. Probability values always fall between 0 and 1. A probability of 0 means an event will never happen. It's impossible. A probability of 1 means the event is guaranteed to happen. It's certain. Everything in between represents varying degrees of likelihood. Let's apply our formula to a common example. When rolling a standard six-sided die, there are 6 possible outcomes, the numbers 1 through 6. If we want to find the probability of rolling a 6, we have just one favorable outcome, getting a 6 out of 6 total possible outcomes. So the probability equals 1 divided by 6, or approximately 0.167. Now let's look at flipping a fair coin. There are 2 possible outcomes, heads or tails. If we're interested in getting heads, that's one favorable outcome out of 2 total possibilities. The probability equals 1 divided by 2, which is exactly 0.5 or 50%. This is why we call it a 50-50 chance. Each outcome is equally likely. Probability gives us a powerful tool for making predictions and informed decisions in uncertain situations. From weather forecasts to games of chance, understanding the likelihood of different outcomes helps us navigate an unpredictable world with more confidence and clarity. When we talk about probability, we're measuring how likely something is to happen. The fundamental formula for probability is written as P of E equals the number of favorable outcomes divided by the total number of possible outcomes. This fraction gives us a value between 0 and 1 that represents how likely an event is to occur. Let's use a 6-sided die to understand this formula better. A die is perfect for explaining probability because it gives us a fixed number of equally likely outcomes. When we roll a die, each face has an equal chance of landing face up. On a standard 6-sided die, we have the numbers 1 through 6, with each number appearing exactly once. Here we can see 3 of the faces, showing 1, 3, and 6. Let's highlight each face to understand our possible outcomes better. When we roll a die, any one of the 6 faces could land face up. Each one represents a single outcome in our sample space. To apply our probability formula, we need to identify 2 things. What are our favorable outcomes, meaning the outcomes we're looking for, and what is the total number of possible outcomes overall? Let's say we want to find the probability of rolling a 3. First, we need to identify our favorable outcomes. These are the outcomes that satisfy what we're looking for. In this case, there's only one face with the number 3 on it, so we have exactly one favorable outcome. Next, we need to count the total number of possible outcomes. A standard die has 6 faces, numbered 1 through 6, so there are 6 possible outcomes when rolling the die. Every time we roll, exactly one of these 6 faces will land face up. Now we can calculate the probability of rolling a 3. We have one favorable outcome divided by 6 total possible outcomes, so the probability equals 1/6, or approximately 0.167. This means that if you roll the die many times, about 1 out of every 6 rolls should result in a 3. This example illustrates the core idea of probability. It's always a ratio comparing how many ways we can get what we want to the total number of possibilities. The same formula works for calculating probabilities in many real-world situations, like drawing cards, picking marbles from a bag, or even predicting weather patterns. Let's understand probability with a simple example of rolling a die. Probability helps us measure how likely an event is to occur. The basic probability formula states that the probability of an event, which we write as P of E, equals the number of favorable outcomes divided by the total number of possible outcomes. This formula allows us to calculate the likelihood of any event. A standard six-sided die has faces numbered from 1 to 6. When we roll this die, each face has an equal chance of landing face up. This is what we call a fair die. Let's say we want to find the probability of rolling a 3. This becomes our event of interest, or our favorable outcome. We need to count how many ways we can get this outcome compared to all possible outcomes. Looking at our die, there is only one way to roll a 3, since only one face of the die has the number 3 on it. So our number of favorable outcomes is 1. For the total number of possible outcomes, we need to count all the different results we could get when rolling the die. Since our die has 6 different faces, we have 6 possible outcomes when we roll it once. Now we can apply our probability formula to calculate the probability of rolling a 3. We have one favorable outcome divided by 6 total possible outcomes, giving us a probability of 1 divided by 6. The numerator in our fraction is 1 because there is exactly one way to roll a 3 on our die. This represents our single favorable outcome that satisfies our condition. The denominator in our fraction is 6 because there are 6 possible outcomes when rolling a die. These represent all the possible faces that could appear: 1, 2, 3, 4, 5, or 6. Therefore, the probability of rolling a 3 on a fair die is 1/6, which can also be expressed as a decimal, 0.167, or as a percentage, 16.7%. This means that if you roll the die many times, you can expect to see a 3 about 1/6 of the time. This example demonstrates how we can use the probability formula to calculate the likelihood of discrete events like rolling a specific number on a die. The same formula can be applied to many other situations, like drawing cards, picking marbles from a bag, or even predicting weather patterns. Let's explore the fundamental probability formula. This formula states that the probability of an event equals the number of favorable outcomes divided by the total number of possible outcomes. To understand this concept, let's use a standard deck of playing cards as an example. A standard deck contains 52 cards total. A standard deck has 4 suits: hearts, diamonds, clubs, and spades. Hearts and diamonds are red cards, while clubs and spades are black. There are 13 cards in each suit, giving us 26 red cards and 26 black cards total. Now let's calculate the probability of randomly drawing a red card from this deck. When we draw a single card, there are 52 possible outcomes because there are 52 cards in the deck. For our event, drawing a red card, the favorable outcomes are all the hearts and diamonds. As we highlight them here, you can see there are 26 red cards that would satisfy our condition. To find the probability, we need to identify the number of favorable outcomes and the total number of possible outcomes. We have 26 red cards that count as favorable outcomes out of 52 total cards in the deck. Now we can apply our probability formula. The probability of drawing a red card equals the number of favorable outcomes, 26, divided by the total number of outcomes, 52. Simplifying this fraction, we get 26 divided by 52 equals 1 divided by 2. Let's simplify our visualization to focus on the final probability. The probability of drawing a red card from a standard deck is exactly 1/2, which means there's a 50% chance of drawing a red card. This makes intuitive sense because exactly half of all the cards in the deck are red. This example perfectly demonstrates our probability formula in action. We found the number of ways our desired outcome could happen, which was 26 red cards, and divided by the total number of possible outcomes, which was 52 cards in the deck. Anytime we can count the number of favorable outcomes and the total number of possible outcomes, we can use this formula to calculate probability. In our card example, the probability is 1/2 because the number of red cards and the number of black cards are equal in a standard deck. In probability theory, all probabilities must fall between 0 and 1. This constraint is one of the fundamental rules that makes probability work as a mathematical tool. Let's visualize this constraint using a number line from 0 to 1. This scale will help us understand where different types of events fall in terms of their likelihood. At 0 on our number line, we have impossible events. These are things that can never happen, no matter how many times we try. They have 0 chance of occurring. At 1 on our number line, we have certain events. These are things that will always happen, every single time, without fail. They have a 100% chance of occurring. This gives us our key constraint in probability. The probability of any event, which we write as P of E, must be greater than or equal to 0 and less than or equal to 1. This makes intuitive sense. An event can't have a negative chance of happening, and it can't have more than a 100% chance either. Let's start with an example of an impossible event. Consider rolling a 7 on a standard 6-sided die. If we look at a regular die, the faces only show numbers 1 through 6, so getting a 7 is simply impossible. To calculate this probability, we use the formula: number of favorable outcomes divided by total number of possible outcomes. Since there are 0 ways to roll a 7 and there are 6 possible outcomes when rolling a die, the probability is 0 divided by 6, which equals 0. This event sits exactly at the 0 point on our probability scale. On the opposite end of our scale, we have certain events with a probability of 1. Consider drawing any card from a standard 52-card deck. No matter what, you'll always draw a card. It's impossible to not draw one if you're drawing from the deck. Using our probability formula again, there are 52 favorable outcomes since drawing any card satisfies our condition, and there are 52 total cards in the deck. So the probability is 52 divided by 52, which equals exactly 1. This represents absolute certainty. The event will always occur. Most events in probability fall somewhere between 0 and 1. For example, consider rolling a 3 on our standard die. There's exactly one face with the number 3 out of 6 total faces. So the probability is 1 divided by 6, which is approximately 0.17, or about 17% chance. Another example is drawing a red card from a standard deck. In a deck, half the cards are red, the hearts and diamonds, and half are black. So there are 26 red cards out of 52 total cards, giving us a probability of 26 divided by 52, which simplifies to 1/2 or 0.5. This represents a 50% chance, right in the middle of our probability scale. Notice how each of these probabilities can be positioned at a specific point on our number line. The die example sits at about 0.17, while the red card example sits exactly at 0.5. This visual representation helps us understand the relative likelihood of different events. To summarize what we've learned, all probabilities must be between 0 and 1. An impossible event has probability 0, a certain event has probability 1, and all other events fall somewhere in between. The closer to 1, the more likely the event is to occur. The closer to 0, the less likely it is. Understanding this fundamental constraint is essential for working with probabilities in real-world scenarios, from weather forecasting to games of chance. It provides a consistent framework for measuring uncertainty in a meaningful way. Let's quickly recap what we've learned about probability constraints. The probability of any event must be between 0 and 1 inclusive. Impossible events have a probability of 0, possible events have probabilities greater than 0 and less than 1, and certain events have a probability of exactly 1. These constraints give us a standardized way to measure and compare the likelihood of different events. Complementary events are a powerful concept in probability that help us understand what happens when an event doesn't occur. Let's use a standard deck of playing cards as our example. In a deck, cards come in 2 colors, red and black, with exactly half the cards being red and half being black. If we randomly select one card from the deck, the probability of drawing a red card is 1/2. We write this as P of red equals 1/2. This makes sense because 26 out of the 52 cards are red. Now for complementary events. The complement of an event is everything that is not that event. We denote the complement of event E as E prime. The formula states that the probability of E prime equals 1 minus the probability of E. This makes sense because all possibilities must add up to 100%, or 1 in decimal form. In our card example, the complement of drawing a red card is not drawing a red card, which means drawing a black card. Using our formula, the probability of not drawing a red card equals 1 minus the probability of drawing a red card. We know the probability of drawing a red card is 1/2. So when we substitute this value into our formula, we get 1 minus 1/2, which equals 1/2. So the probability of drawing a black card is also 1/2. This matches what we know about the deck. Half the cards are black. This calculation confirms our intuitive understanding. Probabilities always fall between 0 and 1. Let's visualize these card probabilities on a probability scale, where 0 means impossible and 1 means certain to happen. For our card example, both the probability of drawing a red card and the probability of drawing a black card equal 1/2, placing them right at the midpoint of our probability scale. Notice how these probabilities connect directly to our red and black card groups. Together, they account for all possible outcomes when drawing a single card. This leads us to an important principle. The probability of any event plus the probability of its complement always equals 1. Written mathematically, P of E plus P of E prime equals 1. This formula is extremely useful in probability problems. When it's easier to calculate the probability of an event not happening, we can find that, and then subtract from 1 to find the original probability we're looking for. Complementary events represent all the ways something can either happen or not happen. Since these cover all possibilities with no overlap, their probabilities must sum to 1. The key takeaway is that for any event, the probability of it happening plus the probability of it not happening must equal 1. This is the fundamental principle of complementary events, and it works for any probability problem you'll encounter.